Hello, all. I know it seems like most of my lectures I've been giving to you this semester have been from a hotel room, but it is what it is, and we do the best that we can, right? So our new chapter that we're going to be doing this time around is about the solar system, um, and it's a pretty long chapter, but we split it up, or the PowerPoint is pretty long, but we split it up in 2 days, so it shouldn't be that bad. So let's go over the learning objectives real quick. In this chapter, in this lesson, we'll learn about astronomy, the universe, the Milky Way, the solar system, and the sun. We'll talk about the electromagnetic radiation, which we talked about already before, but just a quick little review. We'll talk about Kepler's laws, also describe planet classifications and orbits. We'll talk about albedo, the Earth's rotation and stellar parallax, and an aberration of starlight. We'll also identify and describe terrestrial planets, Jovian planets. We'll probably stop there when we get to the planets and do the rest when we come back on Tuesday. So we'll go over on Tuesday the terrestrial planets, the Jovian planets, the dwarf planets, describe the outermost reaches of the solar system, describe the formation of our solar system, describe other systems outside of our solar system, and then also identify a star wobble, right? So again, kind of long, but we're probably going to stop the video right about here, right before terrestrial planets, or maybe we'll go over the terrestrial planets. We'll stop at the Jovian planets. Okay. So let's start out by talking about what astronomy is. Astronomy is a scientific study of the universe beyond the Earth's atmosphere. The universe is everything that includes all energy, matter, and space, right? And so in our universe, there are about 50 billion galaxies, and we are one of those galaxies. That's the Milky Way galaxy. And then our solar system, which is inside the Milky Way galaxy, contains one sun, or star, which is our sun, and then 8 planets, which is very sad because we used to have 9 planets, and we'll talk about that later, and then 4 dwarf planets, tons of asteroids, comets, meteoroids, and then of course the sun supplies all the energy for our planet. So here's your first question. Go ahead and just scan it and answer the question on your QR code. And if it doesn't work, then just send me a Teams message with the answer, so I know that you actually watched the video. What is the name of our galaxy? If you don't know what's literally on the previous page. Anyway, so that's the question for today. Okay. So let's talk about the electromagnetic spectrum real quick. Remember that the electromagnetic spectrum is everything from gamma rays all the way down to radio waves, and then all the stuff in between, right? So I think we talked about this before. Oh, we actually did talk about this before. Gamma rays, and then X rays. Those are the strongest. Ultraviolet. Remember, gamma rays can cause the Hulk. We use X-rays to see our bones. Ultraviolet's pretty strong too. Can cause cancer. Then we have visible, which is Roy G. Biv. We talked about that a lot. And then infrared, microwaves, and radio waves. So why do we need to talk about this again in the universe or the solar system chapter? Well, it's because we use electromagnetic radiation or light from the universe, like out in space, so we can try to figure out what kind of material is out there, like what kind of what stars are made of, what other planets are made of. Because remember, depending on the elements or the atoms that are present in the different celestial objects, um, they'll give you a different color, right? Remember, the only problem we have, though, and we'll talk about this a little bit more later, is that we have detectors on Earth, right? Like electromagnetic radiation detectors and telescopes on Earth, but they're kind of hard to use sometimes because the atmosphere can block a lot of what we're trying to detect. So we also have telescopes out in space, and the main one is the Hubble Space Telescope that's sitting out in space, and that thing's taking a lot of incredible pictures of our solar system and the universe too, like the rest of our galaxy. So let's talk a little bit more about our solar system. It's a complex system of moving masses held together by gravitational forces. Obviously, the sun is the center, which is ironic because we didn't always believe that. The sun is also the dominant mass. So, what does that mean? It means it's the biggest thing in our solar system. And then, revolving around the sun is 8 major planets with over 170 moons, 4 dwarf planets, and 1,000 other objects like asteroids, comets, meteoroids, and a partridge in a pear tree. No, I'm just kidding. So, back in the day, there were 2 models of the solar system, and I told you that back in the day we didn't think the sun was the center of the solar system, right? So back then they actually thought that the Earth was the center of the solar system, right? And so the guy named Ptolemy thought this, and he called it the geocentric model. And in the geocentric model, the Earth was the center of the solar system, and the stars and the sun rotated around the Earth, and the Earth didn't move around at all. Turns out he's wrong. The right model is called the heliocentric model, and it is centered where its claim is that, which is a correct claim, is that the center of the solar system is actually the sun. And this was brought up by this was theorized by Nicholas Copernicus, and so he was right. The sun is definitely in the center, right? Although we have a lot of, I don't know if you remember a couple of years ago, there's a lot of people out there that were called like flat earthers, and they thought that the Earth was still the center of the universe and the Earth is flat. Don't even get me started about that. So, anyway, our next question is, which of the following is not true about our solar system? Is it that it's a complex system of moving masses held together by gravitational forces? The sun is the center? The sun is the dominant mass? Or all of these true? So go ahead and scan that QR code, answer the question, and if you can't get it to work, then just send me a Teams message so I know that you actually watched the video. All right? So there was this guy named Johannes Kepler, right? Super famous guy. And he came up with the three laws that govern planetary motion. So we call it Kepler's laws of planetary motion. And so the very first law that Kepler came up with was called the law of elliptical orbits. So interestingly enough, we used to think that the orbits around this, the orbits, like the path that planets would go around the sun, was circular. But in fact, they're not circular. They're actually elliptical, right? They're oval shaped, right? So here's a picture of a planet right here going around the sun. And you see the shape that it's going around the sun is actually an oval or an ellipse, not a circle, right? So that's the first law. The first law is that planets move around the sun in elliptical orbits, not in circles, okay? The second law is a little bit more complicated, and what it is it's called the law of equal areas, right? And what it means is that if you have your elliptical orbit, right, and you start, say, the Earth here, right, and the Earth is traveling around the sun like this, right? This is the Earth's elliptical orbit around the sun. If you were to allow the Earth to travel a certain number of days, right, say from here to here, right, in a year, that same number of days on the other side of in 6 months will have the same sweeping area, right? So the area right here between the sun and the Earth's orbit will be equal on both of these, right? So say at the perihelion, which is January 4th, you wait 5 days, right? And you calculate the area that's between the sun and the Earth's orbit right there. And you do the same thing at the amphihelion, which is on July 5th, wait 5 days, and you calculate the area that between the Earth and the orbit of the Earth and the sun. These two areas are the same. We call these sweeping areas, right? And so that would be the law of equal areas, okay? So what is a perihelion? The perihelion is the point on the Earth's orbit that it's the closest to the sun. That's around January 4th. And then the point of the Earth that is the furthest away from the sun is called the amphihelion, and that is on July 5th, right? That's on July 5th. Now, Kepler's third law is probably the most complicated of all the laws. And all that I really want you to know about Kepler's third law, which is called the harmonic law, is that when the orbit of the planet is elliptical going around the sun, there's always these 2 points in the ellipse, right, that we call the foci, right, of the ellipse, right? And so one foci of the ellipse is where the sun is, and it has a mirror on the other side, right? And so that's really all I really want you to know about the third law, okay? And so if we went a little further and talked about it a little further, you could say that the time, right, is equal, the time squared, right, for one revolution around the sun, like one full revolution around the sun for the planet. So if it's Earth, it's a year, right? The time squared equals the length of the semi-major axis, right, cubed times K the constant, which is the same for all planets, which is 1 year for every AU. So again, very complicated. All you really need to know is that in Kepler's third law, there are there's two focus points that are called foci, right? And one of the foci is the where the sun is, and the other one is a mirror that where it's a mirror point in the ellipse where the sun would be if it were over there. Okay, but that's all I'm really asking you about that. You don't need to do all this math. So, which of the following is the best? Which of the following best describes Kepler's second law? Is it that it's the law of elliptical orbits, the law of the perihelion and the aphelion, the harmonic law, or it's all of the above? All right, go ahead and scan that, or send me a picture. I mean, not sorry. Uh, send me the answer in Teams. Okay. All right. So major planet classifications and orbits around our solar system. Again, we already knew that the sun was the main mass, the dominant mass in the solar system. It literally weighs 99.987% of the entire mass of the solar system. The rest of it is only 0.3%, and 50% of that, more than 50%, is actually Jupiter. So Jupiter is really big, right? So the big thing here to know, though, is that there are planets that are smaller than Earth. That's Venus and Mercury. They're known to be inferior, right? And the planets that are larger than Earth are classified as superior. So that's everything after Earth, like Mars, Jupiter, Saturn, Uranus, and Neptune. All planets actually orbit in a prograde motion, which is counterclockwise motion. When you look at it from the top, right? They rotate in a counterclockwise motion around the sun, right? And each planet also rotates in a counterclockwise motion, except for Venus and Uranus, which is kind of weird, right? So all planets will revolve around the sun. Uh, Revolving around the sun means they're like going around the sun. All planets will go around the sun, right, or revolve around the sun in counterclockwise motion when you look at it from the top, right? But if you look at their actual rotation, the planet like turning, right, just like rotating around, uh, they all also do counterclockwise rotation except for Uranus and Venus. They do clockwise rotation, so they actually rotate the opposite direction that they're actually revolving around, which is kind of weird. Kind of weird. So let's talk about the terrestrial planets first. Those are Mercury, Venus, Earth, and Mars. They have a high percentage of massive elements, right? Like iron, those kinds of things, which kind of makes sense because all of the terrestrial planets have land, and the land is made of like a lot of heavier elements. So those terrestrial planets are Mercury, Venus, and Earth, and Mars, right? But then we have the Jovian planets. And the Jovian planets are much larger. They're further out from the in the solar system because they're lighter, so they can travel further. And so those are Jupiter, Uranus, and Neptune, right? And most of their mass is made of gaseous elements, right? Most of theirs is made of gaseous elements. So the planet Earth, right, we're going to start out with the planet Earth because that's our planet. It's the third planet from the sun, right? It's a solid with a rocky body with oceans and an atmosphere. The most of our like the surface of the Earth though is liquid water, which is good for us because we need that to survive. The oxygen-containing atmosphere helps us breathe, and then we have a very temperate climate. Most of our planet we can live and organisms survive. It's a good thing, right? It makes our planet unique because none of the other planets have the atmosphere that is required for life, right? 21% oxygen, right? The rest of it is nitrogen. But then, funny thing, the Earth's crust is made of over 90% our oxygen. And I think I told you that before. It's all silicon dioxide, which is sand, right? Interestingly enough, we always thought the Earth was like a perfect circle. It's actually an oblate spheroid, which is just a big word for an actual like squashed sphere, kind of like a football, right? Because if you were to measure the distance from the North Pole to South Pole, it's actually 12,714 kilometers. But if you measure from the one side of the equator to the other side of the equator, it's actually 12,756 kilometers. So yeah, the Earth is not exactly the same up and down as it is left and right. So we call that being an oblate spheroid. So what is albedo? Albedo is the fraction of sunlight that is actually reflected by an object in the atmosphere, right? So if you were to look at Earth's albedo is actually 33%. So if you were, for example, in space and you saw the sun's light bouncing off the Earth's atmosphere and hitting back to you in your eyes, it'd have an albedo of 33%. But if you are standing on Earth, you can't see the Earth be reflecting the sunlight, but you can see other objects in the sky reflecting the sun's light. And so the moon's albedo is actually 7%, right? It's actually the brightest object in the sky. But interestingly, the only reason why it's the brightest object in the sky, is because it's so close to us. But then if you talk about Venus's albedo is actually 76%, and it's the third brightest in the sky. If Venus were closer to us, it would be super bright, right? But yeah, that's like the only reason why. If the moon were not so close, it wouldn't be so bright, and Venus would be the most brightest thing in our sky. And Jupiter is actually out there too. On good days, you can actually see Jupiter out there, and sometimes Saturn, and all that is called albedo. If you didn't already know this, right, the Earth's rotation is actually not up and down; it's actually tilted, right? It's tilted on its axis and it rotates around on its axis. And so uh, the way we know that is actually because you can use a pendulum, right? This is at like the museum. You can use a pendulum and you can swing it back and forth. And since the Earth is rotating on its axis, right? This is called a Foucault pendulum, by the way. As the day goes by, right, because the Earth is rotating, the pendulum will swing back and forth and start knocking down all the different dominoes, right, all around in the circle because the Earth's rotation as it rotates throughout the day. There's this thing called stellar parallax, and I think that the thing that most people uh, will think of when we talk about stellar parallax uh, is that when you if you look at your thumb, right, like this, and you close one eye and you close the other eye and you open it back and forth, right, it looks like your thumb is moving, but in fact your thumb is not moving. It is just that your left and right eye, are seeing the your thumb in a different perspective, right? Different point of view. And so that's why it looks like it's moving, even though your thumb's not moving. So the same thing happens, right, in space, okay? And so the sun is here, right? And the Earth is here, and then there's a nearby star that's reflecting that's producing light, right? And sometimes when the Earth is over here, that's like when you have your left eye open, right? The star's position is over here. But sometimes when the Earth is over here, which is going to be your right eye, the star is over here, right? And so it's just like if you were if the star were your thumb and you were to open and close your left and right eye, it looks like it's moving, right, back and forth. The same thing happens with the Earth as it's revolving around the sun, right? As it's revolving around the sun, uh, the position of stars will be different depending on where it is in its revolution on its orbit around the sun, right? So that's called stellar parallax. So your next question is, which of the following is not true about Earth? The Earth is the fourth planet from the sun. It is a sub B. Is it B? Is a rocky, solid, spherical rocky body with ocean atmospheres? Is it C? Large amounts of surface water in all three phases, or is it D? An oxygen-containing atmosphere? So which ones of these is not true? So that takes us to talking about the aberration of starlight, right? And it's kind of proof that we have orbital motion, right, of the Earth, where the Earth actually moves around in orbit around the sun or revolves around the sun. Because if the Earth weren't going around the sun like we claim, then the stars would be in the same position all the time, right? But we know that when the Earth revolves around the sun, right, we see different celestial objects in different positions. Okay, and so that's called the aberration of starlight. Okay, so one of the things that they used in sci-fi a lot, especially in Star Wars, is the term parsec, right? And if you remember in Star Wars, if you ever watched the movie Star Wars, Han Solo says that he can do the Kessel Run in less than 12 parsecs, right? And so I think the thing that people get confused with is that since it says parsecs, they think it's like a time thing, right? It's actually like a distance thing, right? It's a distance thing. So what is a parsec? A parsec is actually equal to about 3.26 light years. And again, people hear the word year and they think it's a time thing, but it's a distance thing, right? So a light year is the amount of light, sorry, the distance that light will travel in 1 year, right? And light will travel a really long distance in 1 year, by the way, if you didn't know. It will travel a really long distance. So light is very, very fast, right? So 1 parsec is equal to 3.26 light years. And so this is where the word parsec comes from, right? It comes from the word parallax, right, which we talked about a couple slides ago, and second. And so when Han Solo is saying that he can do the Kessel Run to pick up the spice in 12 parsecs, what he's actually saying is that it's not taking him less time. Well, it does take him less time, but the reason why it's like taking him less time is because he's taking a shortcut, right? Like you can go the long way, the scenic route to get to a place, right? But he found a shortcut that was only 12 parsecs, and which is a distance, right? So I think the thing that you really should know is that a parsec is a distance, and so is a light year, also a distance. Don't get confused because it's a second, like that means that it's a time, or it means light year, which means a time. It's not. Those are both distances. Okay. Continuing on though, let's talk about each of the terrestrial planets. Right. Again, those terrestrial planets are Mercury, Venus, Earth, and Mars. Right. They're very small in size. The reason why though they're small in size is because they're made of like solid elements. Solid elements, right? That are heavier, and since they're heavier, they can't travel that far out of the solar system, right? And so that far into the solar system, and that's why most of the planets beyond Mars, or all of the planets beyond Mars, are mostly made of gas, right? So they're very small. They're close to the sun, right? They have no rings. Only Earth and Mars have moons, and only Earth has surface water and oxygen. Uh, People, though, not people, but like astronomers and people in the space community, right? They have actually found remnants of frozen water on Mars, right? And so there's things out there right now on Mars, like uh, is it the Pathfinder mission? Uh, Damn, I can't remember what it is now because I mean I have the Lego set too, but they have a robot out there on Mars, and the robot is going around collecting samples, and it's actually really cool. I think I have pictures from it later, so we'll get there. So the formation of the terrestrial planets, right? Like I was saying, most of the planets out further in the solar system, right? They're mostly made of gas, and the reason why is because helium and hydrogen are actually the most uh, they're the most abundant elements in the universe, right? And because they're the first and second element. And so, whenever the terrestrial planets were forming, and also when the rest of the planets were forming, elements that were super light would travel way further out into the solar system and form planets out there, whereas the heavier elements stayed closer to the sun because they were too heavy to travel that far, right? And so that's why most of the planets that are terrestrial are made of very heavy elements. It's just because they couldn't travel as far; they weren't as light. But then all the other planets beyond Mars are mostly made of gases, and those gases are like helium and hydrogen. And because they were lighter, and they could go further into the solar system to form planets out there. And we'll talk about that when we get to the Jovian planets. So Mercury is the first terrestrial planet. It's the closest planet to the sun. It's got a very, very short year, right? Or revolution, period of revolution. It's only 88 days. Can you imagine that? Can you imagine if our year was only 88 days long? Man, that'd be crazy. Uh, Hell, this class would already be over. Mercury was named. Mercury is also named by early Greeks after the swift messenger of the gods, right? But the interesting things about it is that Mercury is so close to the sun that the surface is like 473 degrees Celsius. That's freaking hot, right? But then that's on the side that's facing the sun. On the side that's the dark side on the dark side, it's still pretty hot at 173 degrees Celsius, right? But since the Mercury is so close to the sun, it's so hot that it can't hold an atmosphere, right? It has no atmosphere. Um, Interestingly enough, it rotates 3 times while circling the sun twice. Interesting, right? Crazy stuff. The next planet is Venus. Venus is actually the closest planet to the Earth, and it's the third brightest object in the sky. Um, second to the moon. Again, if the moon were not there, it'd probably be Venus. Venus would be the brightest. And so, due to its brightness, it's named after Venus, the goddess of beauty, the Roman goddess of beauty. Right? When you look at pictures of Venus, it actually looks like Earth, but it's very, very hot there. And there's a whole bunch of CO2 there, right? And so nothing could live there, even though on the outside it looks like Earth, right? And so part of the reason, it's closer to the sun, so that makes it already hot. But then the atmosphere of CO2 of Venus is made of 96% CO2, and so that's like a greenhouse gas. It makes it super hot there. So the temperatures reach all the way up to 477 degrees Celsius on Venus. Right, very sad because it's a very pretty planet from the outside, but it's very extreme on the inside. So you can't really live there. Again, so Venus is one of those planets, right? That even though it revolves around the sun counterclockwise, it will actually rotate against that, right, and go in a clockwise motion when it's rotating. Crazy stuff. I guess another cool fact too is that the atmosphere of Venus actually rotates faster than the solid planet. I'm not even sure how that works. All right, next question. Venus, uh, Venus, a witch? Obviously a typo there. So sorry, but it says which of the following is not true about the atmosphere of Venus? It's made of 96% CO2. It has a pressure of 1 atm. It's as hot as 477 degrees Celsius, or all these statements are true, right? And again, if you don't know the answer, it's on the previous slide. So we've already talked about Earth, so let's talk about Mars now. And so the first thing to notice about Mars is that it's a red color, right? And the reason why it's actually red color is because it's covered with iron oxide, which is rust. Named after the Roman god of war. I think that the two things that are really interesting about it is that it has two polar ice caps that are frozen, right? So during the wintertime, during the Mars winter or the Martian winter, right, it's so cold that the ice caps are composed of frozen CO2, right? But then when the summer comes around, it's actually mostly CO2 vapor with frozen water in the summer. So scientists have discovered there's frozen water on Mars, but I think they've yet to find any actual life on Mars, like maybe bacteria. I don't know. I'm not sure. But yeah, the red color is due to iron oxide, which is rust on the Earth's on Martian surface. So here we go. So in 1997, right, pictures of the Martian surface were sent to Earth from a rover called Sojourner, right? And then in 2004, Spirit and Opportunity also landed on Mars, right? And once had water, and found that Mars once had water on the surface. And then in 2005, the Mars Reconnaissance Orbiter, or the MRO, was launched, and it found subsurface ice, right, amount of water, and so again, we found a lot of frozen water on Mars, but we haven't found any liquid water that can support life yet. Uh, but they're still working, right? And then in 2012, I think this is the one that's currently there right now, which is the Curiosity rover, and it's literally carrying a mobile lab to see if there are conditions that are suitable for microbial life, right? But again, no life has been detected, but scientists are still working. Um, the Martian volcano, Mount Olympus, is pretty cool looking, right? It's the largest volcano in our solar system at 24 kilometers high. That's 3 times the height of Mauna Loa, which I have no idea where that is. It sounds like it's in Hawaii, but a very large volcano, on Earth, right? It's 3 times the size of that volcano. But yeah, like seeing it from space looks pretty cool. And then there's also this really huge canyon on Mars too, called the Valles Marineris, right? And it's 4,000 kilometers in length and 6 kilometers deep. That's freaking deep, right? And so this canyon, geologists think it was made from like a fracture from internal forces inside, like an earthquake type of thing, cracked open, right? So that's pretty cool. And then we'll stop after this question. Which of the following is not true about Mars? It was named after the Roman god of war. The ice caps are composed of frozen methane in the winter. Ice caps are composed of CO2 vapor and water in the summer, or the red color is from iron oxide, right? So go ahead and try to answer that question. And then when we come back on Tuesday, we'll start talking about the Jovian planets, which are Jupiter, Saturn, Uranus, and Neptune. All right, I'll see you on Tuesday.